Hi, welcome to today's lesson on solving systems of linear equations by substitution. This is actually the second video in the series, and we're going to finish it up with a real challenging problem. Okay? So again, when we solve systems of linear equations, we're looking for where do the two lines intersect on a graph, even if we don't do it graphically. Okay, we always want to keep in mind that that's what we're finding. Where do they meet graphically? Okay, like where do these things meet in the real world? If two things are flying at each other, where do they collide? And that may be very important to us in whatever career we choose. Okay, we also want to know that this works when the equations aren't linear. Okay, right now we're going to deal with linear equations. They're the easiest, they're the most straightforward, if you'll pardon the pun. They're straight. They land, boom. But at some point you may have something that's doing something like this and you want to know where it hits, or it might be doing something even weirder, who knows, okay? And you're trying to hit something, okay? My favorite would be firing a probe at, say, at the moon. You want to hit the moon, right? The moon's in an orbit around us, which means it's in a circular, and we're trying to shoot something straight at it. Seems a little weird, but that's what we're trying to do, okay? So, again, we would be asked to solve, and again, we could say solve the system, we could say find where the two lines meet, we could say find the solution to this system. I mean, there's lots of ways to say the exact same thing. Where do the two lines meet on a graph? Give me the coordinates, give me the x and the y, give me the point. So, but let's go with a real hard one. Okay, so 2x plus 3y equals 6, and 2x minus 5y equals 14. Now, I'll let you in on a little secret. This problem would be great if we had the method called elimination, which is the next lesson that we're going to do. But I always like to sort of set us up for, wow, this would be a lot easier if we had some other method. Now, obviously, graphing looks miserable because, one, neither equation's in slope-intercept form, so that's going to take me a lot of work. Even though this one has kind of nice intercepts, this one has horrible ones. Okay, 14, this would be like 14/5, or if I turn it into a slope-intercept form, I've got 2/5, and I'm trying to plot where is the point 14/5, and yeah, awful, okay? So terrible for graphing. They're actually not, it's not great for substitution, it's okay. It's great for elimination. And that's the thing. Again, that's why when we start showing you 2 and 3 and 4 different ways to do a problem, it's so that you can say, you know what, fortunately, I can use this method here, and I can use this method there, and this one's easier now, and this one's easier here, and you can make those kinds of decisions, okay? So fortunately, or unfortunately, this one's great for the next method up. But I find you don't really appreciate the next method up if you haven't struggled through doing it with the harder methodology. So doing this using substitution, when you see elimination, it's going to be like, oh, why didn't you show us that first? That one's great. I like that one. That one's my favorite right there. And I can assure you that's what's going to happen. But part of what makes that really great is doing it the hard way first. So let's do substitution. So the first thing we have to do is we have to isolate the variable in one of these two equations, in one equation. Now, which variable we isolate and in which equation does not make any difference to us. The only thing that really determines which one we do is which one looks the easiest. So I would opt for the 2 here because it's the smallest, and because these are smaller rather than these two. Also, there's no negatives here, so that seems like it would be easier to me. I could be wrong, but that seems the easiest to me, okay? So that's what you want to do. So I'm going to take 2x plus 3y equaling 6, and I'm going to isolate x. I'm going to get x all by itself. So first I'm going to subtract this 3y. 2x equals negative 3y plus 6. And then I'm going to divide everything by 2. And I get x equals negative 3/2 y plus 3. Okay, well, not ideal. I don't like fractions much, either. But it is what it is, and it's at least this was a whole number. So if And this is not slope-intercept form because it's x equals y, not y equals x. X equals m. It doesn't. This is not a form that we have a name for. But I've done it. I've isolated one of the variables. And now I can take this and I can replace this x with all of that in this equation. So let's do that. So 2 times -3 halves y plus 3 minus 5y equals 14. Ugh, what a mess. I got fractions, I got distributed fractions, but you know, it still beats graphing, I can assure you. Graphing, you'd be trying to figure out where is 14/5 on a graph. I have no idea. I don't think I have that kind of eye for it. Couldn't pinpoint that. Okay, so now I do my distributed property. 2 times -3 halves. Well, these 2's reduce, and I'm left with -3y. 2 times 3 is 6, minus 5y equals 14. I can combine my like terms here. I've got -3 and -5, so that's -8y plus 6 equals 14. Subtract the 6, -8y equals 8. Hey, I at least made my life a little easy. And I get y equals -1. Whew. That was a lot of work to get y equals -1. I mean, you can see how much work I've done. And I haven't even gotten the answer yet. I'm only halfway, I'm most of the way done with the problem. I would say the big first step there was isolating the variable. The second big step was plugging it into the other equation to find the y value. And now I can plug this y equaling -1 into either equation. They better give me the same answer. So again, I'm going to plug it into both just to be sure, okay? Because I want to be able to ask both equations, where do you intersect? And they better tell me the same thing, because right now they are essentially, because I put them together, they both are telling me we're at this -1 on the y. So I'm going to erase this. I'm going to bring that y equaling -1 up here. And then I'm going to split it down the middle right here. So I'm going to 2x plus 3y equals 6 here, and 2x minus 5y equals 14 over here. And I'm going to plug in -1. And these two better give me the same result. If they do, then I know I've done it correctly and I can feel good about my answer. So 2x plus 3 times -1 equals 6. 2x minus 3 equals 6. Add 3 to both sides. I get 2x equals 9. I divide by 2, and I get x equals, and I could leave it as a fraction, but I think for purposes of this particular problem, I'm going to turn it into a decimal. 4.5. No mixed numbers. We don't do mixed numbers. Decimals are preferable sometimes to fractions. It's a little easier for me to visualize where I would be on a graph, 4.5. That would be, again, that's not terribly graph worthy. I'm not really fond of trying to graph something that's at 4.5, but I'd be okay because it's that right in the middle of between 4 and 5. But this better give me 4.5. I already feel uncomfortable with that answer, so I better make sure it works. So again, 2x minus 5 times -1 equals 14. 2x, -5 times -1 is positive 5. So I'm going to subtract the 5, and now you can see I'm already down here at 2x equaling 9, so I'm sure I'm right. So not a very desirable answer, but let's be honest. If I just threw an object, if I said, hey, where do these two things meet? And I didn't tell you anything, and I just sort of threw them in, what would determine, I mean, why would you expect them to come out as nice, neat, whole numbers? It'd be nice. It's nice when they do work that way, okay? But in truth, the whole number could be anything, okay? It could, or the point where they meet could be anything. Now, in the first set of equations I was solving for y, I was getting into slope-intercept form, and in these, every time I solved for x, doesn't matter which variable you isolate. That's a choice that you make, okay? Because you are going to start, and you'll look. Is the coefficient 1? That's the one I want to isolate. Is the coefficient -1? That's my second choice, because that'll guarantee me nothing but whole numbers, really. Is there something if is that not an option, then I start looking at, well, which one looks smaller? Or is there something that looks obvious, like it's 3, 6, and 9? Ooh, those would all be divisible by 3. I'd like to do the one that has the 3. Or 2, 4, 6. They're all divisible by 2. I'm going to pick the one with the 2. This was as good as I could do, and I had to deal with fractions to do it. And again, I assure you, part of what makes this worth struggling through is so that when I show you elimination next set of lessons, if you go ahead and take a look at those lessons, you'll be like, well, that method is just better. That method is just easier. Why would anybody want to use those other methods ever? And part of the answer to that ever part is this works when one's linear and one's not. So if you have that idea of an object that is doing what we call a parabola, which is sort of like if you take an object and threw it in the air and it came back down, this little curve, that's not a straight line, it's curved, it's up and it's down. Well, what if you wanted to hit it right at that highest point? Well, what is that line? Where does that happen? So now you have one equation that's linear and one that's not, and you're still trying to figure out where they intersect. That can be done using substitution. It's hard, don't get me wrong, but it will be something you can do, and you will be asked to do it. Oftentimes you'll get to do it in a math class, sometimes you do it in a physics class, because of what I just suggested, that idea of like throw an object up and when you want to hit it right at a certain point, or what's the math behind that, okay? And then you can extrapolate that into much more complicated things. Remember at the beginning I talked about trying to hit the moon. The moon is moving in an elliptical orbit, not really circular, it's actually elliptical, and you want to hit it because it's never going straight. It's always curving, but you're going to shoot straight because we don't have a shoot curve, So we're going to, and if we did, we'd have 2 curve equations, and we'd be trying to line those both up and figure out where they intersect with one another. Okay? So when it comes to substitution, so let's break it down into tasks. Okay. So we're solving by substitution. Again, because we're substituting part of one equation for another, and then when we're done with that, we're going to get a result. We're going to substitute that back into the other equation to find the missing coordinates. So the first thing we're going to do is we're going to isolate one variable in one equation. Now that may already be done for you because they may give you an equation in slope-intercept form, or they may just, for whatever reason, give you an equation with one of the variables already solved for you. And that's usually the first couple of problems you'll see on almost any homework assignment. They're going to start with the easier ones, the ones where that's already been done for you. Okay? Then they'll start to ask you to do more. Oh man, I'm not going back. Okay, ignore that shaking for a moment. Okay, they're not going to go back. They're not going to make it easier for you. Okay, so they're going to be asking you to solve for more and more, isolate harder and harder variables. So you start by isolating one variable in one equation. Then substitute the result in the other equation. Okay? So you're going to get a value, something like y equals 3x plus 1. Then you're going to replace the y with 3x plus 1 in the next equation. And then solve for the remaining variable. So now that you can see there's only x in this one. And when you're done with that, we then use the solution to find the other coordinate. So in this case, we would have solved for x. We would then use this, whatever we got here for x, to find y. Okay, so that's the process. That is the how to solve a system of linear equations by substitution. Okay, it has applications beyond just linear equations. It has applications in science as well as later math classes. And it's a method that works a little bit better for solving when graphing is too hard. More that, not so much that it's hard, but that if the point where they intersect is something that is going to be impossible to identify, like I said, 3/7 or 2/3 or 3.1. Oh God, what if it were, something like 1/10? You'd have a really hard time figuring that out. You can do that mathematically, not so bad. It's a little bad, but it's not horrifically bad. And again, when we get to the next one and you see elimination, you're going to be like, why do we even bother with those other two? They have other applications outside of just linear ones. But that's what we're headed. That's what's next. And ignoring that little wavery part, I will see you in class or in office hours.